All right. So today our goal is to think about a little bit more deeply what it means to be a maximum or a minimum of a graph. Okay. And yesterday we talked about sort of an application of it, that if we wanted to have the least amount of material or the most amount of revenue, how could we use calculus to find that? And so today we're going to go a little bit in the opposite direction. We're going to go a little bit more conceptual and theoretical, using these same concepts, but thinking about how it applies to graphs in general. Okay. And so in 4.3, we're going to take a look at some definitions, review some ideas that maybe we've seen in the past, but maybe hasn't been completely clear to us, or that we haven't seen in a while. Okay. So for 4.3, it is titled Maxima and Minima. And a maxima is just plural of the word maximum. So if you have one, it's a maximum. But if you have like two or three or more, it's a maxima, like all together. All right. So it's not a different word. It's just the plural form. Of maximum and minimum. Okay. And so let's talk a little bit about what we know. All right. So one thing that we know is the vertex of a parabola. And I know that yesterday folks were able to describe, and throughout the course, anytime we have a parabola, if we have a regular upward facing parabola, we know that there is a minimum here. And that minimum has a slope of 0. And we've also looked at the upside down parabola, right? When the quadratic term is negative. And that term, or that graph, does not have a minimum, but it has a maximum. And at both the minimum and the maximum, we have slopes of 0. Okay. Now, in general, though, maybe way back in pre-calc, you encountered this idea of different polynomial functions. And so in particular, thinking about cubic functions, maybe looking something like this. How many points on the cubic function do you think there will be a slope of 0? Yeah, this one looks like it has 2, okay? And we could see that it would be sort of right at the top of this bump and right at the bottom of this bump. But if we remember some of the other polynomial functions, turns out that with every degree that we go up, we sort of gain an extra bump. And so something like this could actually be a 4th degree polynomial. And how many places on the 4th degree polynomial do we have a slope of 0? Yeah, we have 3, right? We have 1, 2, 3. Okay. Now, yesterday, somebody asked the most wonderful question, which was, how do we tell the difference? How do we tell whether there is a maximum or a minimum? And that's precisely what we're going to get to today. Okay. So what do we know? We want to learn some new vocabulary, and we want to talk a little bit about procedure. Okay. So in particular, we're going to talk about what is an extrema. So that is sort of a new word for us. What are extrema? And not only what are they, but how do we find them? All right, so those would be sort of the 2 pieces that we want to walk away with from 4.3. What are extrema and how do we find them? All right, so let's talk about extrema. All right, so this first question right here says, determine whether each value has a local maximum, a local minimum, absolute maximum, absolute minimum, or neither. And I'm going to tell you right here that if you look at the ends of the graph, you'll notice that there are no arrows. Okay, that there are no arrows. That is intentional. It is on purpose that there are no arrows here. Okay, so that means that we are looking at this snippet of the graph. What we see is what we get. We don't know anything else beyond this, but this is just what we have. Okay. And so knowing that we have these 4 descriptions right here, I'm wondering if we can start to throw out some ideas, right? Let's see, how do we want to do this? All right, local maximum, we'll go with orange. Local minimum, we'll go with this lime green. Absolute maximum, we'll go with this pink. And absolute minimum, we'll go with this light blue. And neither, we'll go with this purple. Okay. So based off of what you think these words might mean, can anyone tell me which one of these X values might be considered? Let's actually start with the pink one, an absolute maximum. All right, which one of these X values might correspond to something that is an absolute maximum? All right, I see 2 answers. I see X equals -1 and X equals -4. Okay, so X equals -1 would be sort of somewhere around here, right? And X equals -4 would be somewhere over here. The key thing about this phrase is the word absolute, okay? So if we think about things that are absolute, in this case, we're thinking absolute maximum, it has to be the highest point in the entire graph, all right? The only way there could be more than one is if they're both at the same height. So knowing that, how might that change our answers? We're looking for an absolute maximum. It means we're looking for the highest point on the entire graph. We want to change that answer to the -4, okay? And so this right here is our absolute maximum, okay? It is the highest point on the entire graph. All right, well, while we're here, why don't we talk about the absolute minimum? All right, knowing a definition and what that word absolute means now, where's that absolute minimum? Good, good, good. Right, at X equals -3, we have the lowest point on the entire graph. And we know because there's no arrows, okay? We know because there's no arrows. All right, let's jump back and take a look at the local maximum. All right, so a local maximum is different from an absolute maximum because a local maximum is just the highest point in that region. It doesn't have to be the highest overall. It's like the highest in the region, right? And I would agree, I think X equals -1 is a very good example of a local maximum, right? Are there any other points that would be considered a local maximum? It's the highest point in that region. Yeah, that very little tail situation happening at the end, that's the highest point in that region, but it's not higher than the pink point. So we can call that a local maximum. All right, good thing I didn't do the minimum yet. Let's change that to a more visible color when I write. Let's change that to regular green. All right, let's talk about the local minimums. Where do we see a local minimum? A point that is lower than everything else in the region. Ah, this one's a little tricky, but if we look right here, we've got just the tiniest little bump coming below the x-axis, right? And so we could call that a local minimum, right? Are there any other local minima? What are our thoughts? Any other local minima? Yeah, I don't think so. There's no other point that's sort of lower than all the rest. Well, we have three x values left, right? In particular, we have x equals -2, x equals 0, x equals 1. And none of those points are sort of the highest in the region or the lowest in the region. And so we're going to call these last 3 points neither. All right. And so knowing this vocabulary would be really valuable, all right? The difference between a local and an absolute, as well as the difference between a maximum and a minimum, all right? So let's see if we can sort of go the other way, all right? And this time we're going to create a graph, all right? So we're going to draw a graph of f of x. This graph is going to have a few features. In particular, it's going to be continuous. We're only drawing from -4 to +4, all right? So we're only drawing from -4 to +4. And it has the following characteristics. It has an absolute maximum at x equals 4. Oh, actually, let's use the same colors from before. What colors did I use? Pink. All right, it is an absolute maximum at x equals 4. It has an absolute minimum at x equals -1. It has a local maximum at x equals -2. And I'm sneaking some new vocabulary in here, all right? New vocabulary. So I'm going to give it a different color. It has something called a critical point that is neither a maximum or a minimum at x equals 2, right? Now, before I ask us to try drawing some of these, I'm going to define what I mean by a critical point. Okay, and I'll type that in the chat so we have that to look at. But a critical point is, it's not a y-intercept. That's a good guess. All right, a critical point is a point on a graph that has a slope of 0, but is not a maximum or a minimum. Okay, so a critical point is just a point on a graph that has a slope of 0. In this case, we're looking for one that has a slope of 0, but it's not a maximum or a minimum. Okay. So here's what I would like to try and do. All right, let's set up a grid. And let's mark off our 1, 2, 3. I don't know why they're so close together. 4, 1, 2, 3, 4. All right. And yes, Matt, that's a great way of summarizing that. We're looking for a horizontal tangent that exists at that point. All right. So where might people start in sketching this graph? Because I think that is in itself a problem-solving strategy, right? We have all this information that we have to sift through. We have to make sure our picture matches that. Where might we start? Okay, so we have a couple different strategies here, right? I really like what Joey's saying. Start with the maximum and the minimum. We know it has to be a high point and a low point. Those are sort of easy to put on a graph. starting with the endpoints, right? So sometimes we start with the two ends and then we sort of connect everything in between. Drawing points, yes, we do want to draw some points, right? But I think one question that I bet a lot of folks have is like, it's an absolute maximum at x equals 4, but like, how high do I draw it, right? And here's the deal, it doesn't matter. It doesn't matter whether your absolute maximum is like all the way up here, or if your absolute maximum is all the way down here. All that matters is that pink point better be, just like Matt said, higher than everything else on your graph, okay? So to sort of illustrate this point, we're gonna start with this pink point up here. It's at the top of my grid, so I can see that it is going to be the highest point of everything else, okay? And so after this, it might feel natural to go to the absolute minimum and draw a point that is lower than everything else at x equals -1, all right? And maybe I draw that like over here. I don't know how low to draw it, but it just should be lower than everything else that I draw. Okay. Well, we have this local maximum at x equals -2. That just has to be sort of a bump, like top of a bump, and it should be higher than that blue point. So maybe I put it somewhere here. All right. And then I'm going to mark off this last special point, the critical point. So a point that has a horizontal tangent. However, this point is not a maximum or minimum, and that's going to be at 2. Okay. And again, I don't really know where that point goes. It just has to be somewhere in the middle of these two. And I know the graph has to sort of flatten out at that point. Okay. And then it's basically a very grown-up version of connect the dots. Okay. So we are drawing our points and then we're sort of connecting them in a way that matches with the statement above. All right. So if we have an absolute max, we have our absolute min, a local max, and a critical point. I'm just going to start drawing here. All right. I know that this has to be a local maximum. So I'm going to make that orange point sort of the top of a bump. And I know that at x equals -1, nothing can be lower than that. So I'm going to go ahead and do something like that. Okay. Now, if I did this to finish off the left-hand side of the graph, that wouldn't be correct, right? Because I have just drawn a part that is lower than the point that I said was the lowest on the graph. So I wouldn't want to do that, but I would want to, I could do anything I want on the other side. It just can't be lower than the blue point and it just can't be higher than the pink point. So I could even do something like this. That would be okay. All right. It does not go below the blue point. It does not go above the pink point. All right. I have no information on those points. I just know that they're there. So this last piece could look very different for different people. All right. How do we connect these last 2 points? I need to get from this absolute min to this absolute max, but I need to sort of take a little rest at x equals 2. And so that might look like, and let's see if I can draw this. That might look like something like this. I'm going to flatten out. Yeah, I'm just going to flatten out for the tiniest bit. And then I'm going to keep going to my absolute maximum. All right. I could have something like this. I could also have the same shape but maybe down lower. So if I do a vertical translation, that would still be okay. I could do the same shape, but flatten out, but a little bit higher. That would be okay. I could make this absolute minimum lower. I could take my absolute maximum and make it higher. So there's a lot of ways to personalize a graph like this, okay? And that's part of what makes it so tricky, is that you could have one that looks sort of different from someone else's, and yet they still satisfy all of the constraints of this that you're asked for, okay? I would encourage you to practice these graphs. I think that it's an interesting way to put together the vocabulary that is a little bit more deep than just memorizing what the words mean, right? If you're able to construct things based on the vocabulary, then you're able to show a deeper understanding of that vocabulary, all right? So let's leave this here. And then let's go on to write down some definitions, all right? So we've talked about an absolute maximum. We've talked about an absolute minimum. How might we define these? Absolute max, absolute min. We can sort of type some guesses into the chat. Good. Absolute maximum. Good. All right. So here's how we typically do these. We usually give the X value only. Okay. And so we're going to say that it is the X value on a graph that has exactly what Luca said. It has the highest point, but let's say has the highest Y value on the graph. Okay, so an absolute maximum is an X value on a graph that has the highest value, the highest Y value on the graph. And we can take this statement and we can modify it just by swapping out one word. What would we change? Yeah, we're going to replace highest with the lowest Y value, right? So from highest to lowest would be the difference between an absolute max and an absolute min. All right. How could we modify the maximum statement to be a local maximum instead of an absolute maximum? What has to change in order for us to have a local instead of an absolute? Yeah, exactly. So we're looking for an X value on a graph that has the highest Y value, not on the whole graph, but in the immediate region. That's not how you spell region. Right? So immediate means like right in that neighborhood. Okay, so it's in the neighborhood of that X value, that Y value is the highest, but it is not the highest everywhere. Okay, and so we could take this statement and we could similarly modify this for the local minimum just by replacing that word highest with the word lowest. Okay. So local maximum is the x value on the graph that has the highest y value in the immediate region. Local minimum is an x value on a graph that has the lowest y value in the immediate region or in that neighborhood. Okay. Now, I do want to make clear what we mean by critical points, because a lot of times, instead of saying, find the maximum, find the minimum, what we're asked to find is the critical points, okay? And so a critical point, we can just say, is the collection of all x values on a graph. All right, so it's a collection of all x values on the graph where two things are true. Right. The first thing that is true is that f prime of x equals 0. Turn that into words for me. What does that mean? F prime of x equals 0.
Slope equals to 0.
Yeah, the slope is 0, right? And in fact, someone said earlier, we're looking for a point that has a horizontal tangent, right? So when that slope is 0, okay, that is one way that you're going to know you have a critical point, okay? And what does that look like? Well, that could be an absolute maximum. It could be an absolute minimum or local minimum, right? We could have a maximum, we could have a minimum, or we can have that new one that we kind of saw in that graph in number 2, where we sort of go up, we flatten out a little bit, and then we keep going up. All right. And so there's sort of a secret point in the middle here where that slope is 0. Right. And I'm going to move this over so I can add one more picture at the end. What might that picture look like? There's one more way that we can kind of visualize where a graph has a slope of 0. It is going to be a critical point still, but I'm wondering what that might look like, right? Because we have sort of this downward facing parabola and upward facing parabola. We have one that has like a positive to a 0 to a positive slope. What might be the fourth picture that would round out this collection? Ah, that's a good guess with the horizontal line. Yeah. It's actually just if we think about sort of instead of positive to 0 to positive, what if we go from negative to 0 to negative? So flattening out, but kind of going in the other direction. Okay. Because when we think about just a horizontal line, yes, that has the slope of 0, but then that would be like every single point. And we're looking for more general cases where we're looking for sort of like a top of a bump, a bottom of a bumper, that one place where the slope is 0. Okay. All right. All right. Okay. So a critical point, right? So a critical point is any of these. However, when we go back to the way this statement was phrased, a critical point that is not a maximum or a minimum. So that second part of that was from this question, but the critical point part is that it has a slope of 0. Like that's it. All right, so let's make this a little bit more clear. Critical point is just where the slope of the function equals 0. Great, thank you. I'm glad you asked, because I don't want anyone to walk away with that misconception there. All right. All right. So we've got some definitions, we've got some pictures. These pictures are going to be super, super helpful, especially when we get to 4.5. Okay. All right. So we're going to talk a little bit about Fermat's theorem. Okay. So Fermat's theorem says that if a function has a local extremum, okay, so this word extremum means it could be a maximum or a minimum. It doesn't matter. We don't know. But we know that it is a local extremum. Okay. So local extremum means max or min. All right. And the other piece that needs to be true is that this function is differentiable at x equals c. Well, that's not a word that we've really seen before. Okay. So one thing that I would like to do is take a moment to define this word differentiable. Okay. So at the root of it, differentiable just means that you can take the derivative. In other words, if something is differentiable, you can find the slope of that point on the function. Sometimes it's easier to think about things that are not differentiable. So if something is not differentiable, it might look like some of the following pictures. Our good old friend, the absolute value function, is differentiable except at one point. Where do you think that point is? Where is the one point on this graph where you cannot find one slope? Yeah, it turns out that's actually going to be at the vertex. Okay. And the reason why is if I said, here's the point, and I want you to draw a tangent line to it, someone might draw a tangent line like this. Someone else might draw a tangent line like this. Someone else might draw a tangent line that looks like this. In fact, every single person in this class and every single person taking math in San Diego Community College District right now, we could all get up there and draw a slightly different tangent line. There's so many to choose from that we say that that is not differentiable because it actually has an infinite number of answers. Okay. If another way to sort of imagine this is on the left-hand side, the slope is -1, but on the other side, the slope is +1, right? So slope goes -1 to +1. I don't know how many of you maybe have people in your life who are like, one moment they're like super happy, super outgoing, and the next minute they're like maybe very angry or very sad about things, and that's sometimes confusing, right? And so this is sort of the mathematical equivalent of that, where you have like negative slope and then all of a sudden it becomes positive and you're like, oh, okay, I didn't know we were going there. How did that happen? right? And so one of the things that we talk about when we're talking about differentiability is that we're looking really for smooth functions, things where that change might happen quickly, but it's not abrupt like the vertex of a absolute value. Okay, so we're looking for smooth, gradual change rather than from the off switch to the on switch right away without any warning. Okay. Now, another sort of common picture for non-differentiable is I feel like when we were all in elementary school, at some point, some teacher asked us to draw like a sunset scene or like, you know, a picture at the beach, and we're all sitting there drawing birds, and all of our birds kind of look like this. Anybody else? Just me? Yeah. So this right here, what you were doing without knowing it is you were drawing a non-differentiable function. All right. How mathematically advanced were you? Like, that's amazing, right? You're sitting there drawing non-mathematic or non-differentiable functions, because for the same reason, we could have a tangent line. But in this case, that tangent line, if we follow the slope, right? This is like slope is here, slope is here, slope is here. And then all of a sudden, right in the middle, that slope actually becomes vertical. And that is a problem for us because we know that the slope of a vertical line is undefined. Okay. So this second picture has a non-differentiable point for a different reason, right? This one, the first one is like, I'm really sad, I'm really happy, right? It's like, it's hard to follow that. The second one is just that at that point, the slope is actually undefined, all right? So anyway, all of this matters because Fermat is saying that if you have a local extremum, meaning you have a maximum or a minimum, and it is smooth, then we know that the derivative of that function at that point is equal to 0. Okay. So let's take a look at these pictures real quick. We have right here in this first picture, does it satisfy Fermat's theorem? Let's see. Well, this looks like a local extremum, right? It is the high point on a graph. And it is a smooth function, right? The slope changes, but it's not abrupt. It's very smooth and gradual. Because this is a local maximum and it is differentiable everywhere, my conclusion is that the derivative at C is equal to 0. The other case that is fitting of Fermat's theorem is case D. All right. I have a local extremum. Yes or no? I do not have a local extremum. Okay. So in this case, this is a critical point, but there's no extremum, meaning it's not a max or a min. It happens to have a slope of 0, but that's not always guaranteed. Okay, that's not always guaranteed. The other 3 pictures are examples of when a function is not differentiable. Okay, so these 2 are both differentiable. So maybe let's put a little circle around those. These 2 are both differentiable everywhere, meaning they're nice, smooth functions that change gradually. whereas these three are not differentiable. Okay, so we have the ones in the pink that are differentiable, the ones in the purple that are not differentiable. So we know right off the bat that these three are not guaranteed to have a slope of 0 at some point. All right. Now, this one fits the bill because there is an extremum and it's differentiable. This one down here, though, even though it's differentiable, it doesn't have the extrema, so it might not be guaranteed. All right, and that's sort of the tricky part with mathematics is we have to make sure things are guaranteed, not that maybe they happen, but for sure they happen, okay? So that's sort of the importance of a theorem is that for sure something has to happen if you can check off both of the things in the checklist, all right?
Can I describe graph D as critical point that is not maximum minimum?
Yes, it is a critical point that is not a maximum or a minimum, exactly. All right, so we're gonna finish off this first part of class by talking about how we find them, okay? We're gonna talk about how we find them. We're also going to revisit this idea of domain, all right? So domain is the collection of all possible x values that can be input into a function, all right? So the domain, and let's write that here, all right? Our domain is the collection of all x values that can be input into a function. Right? So domain is the collection of all possible x values or all x values that can be input into a function. Now, I feel like folks typically have a really bad experience with domain and they're just like, they see the word and they freeze up, kind of like that trig trauma. Like you see a sine or a cosine and you're like, oh my gosh, I can't do this problem, right? And so this is another, if that is you, that's okay. It's okay to be that person, but this is also a point to be aware of and think about, yeah, it might be a hard concept, but how much are you limiting yourself by just saying, I just can't do this problem, right? So a little bit of this, like building that self-confidence, building that idea that like, if you put some time into unpacking something that you might actually be able to understand it, even if it didn't make sense before, okay? I know a lot of you have already grown so much in this class and I'm seeing like different levels of confidence. And I think that is important to embrace that and realize that you are actually a better mathematician than when you walked in on day one, okay? Which means that even if domain was scary before, maybe we can revisit it and see if we know, okay? So let's get started. We have this function, f of x equals 10x over 4x squared plus 1. And the task is to write the domain of the function. The second task is to find the x values of the critical point. And the third one is to think about how we might know if a critical point is a local maximum or a local minimum. All right, so let's take a look at this function. All right, So if we're looking at a domain, the question we want to ask ourselves is actually better to think about what doesn't work rather than what can work. All right. So the question we want to ask ourselves is, are there any X values that will give us an undefined output? All right. Are there any X values that will give us an undefined output? And so one of the things that we should look for, all right, which Matt has already brought up, is that we need to think about, wow, we have a fraction, okay? So we see this fraction in our function 10x divided by 4x squared plus 1. Now, when we see a fraction, there is one way that we can get undefined out. Okay. So with fractions, we get an undefined output when the denominator equals 0. Okay, exactly. So with a fraction, we get an undefined output when that denominator equals 0. That is the only time that will happen. Okay, that is the only time. Therefore, that is the only thing we need to check. All right, so let's grab that denominator. Let's set it equal to 0. And let's see what X values make that an undefined output. All right. So I'm going to subtract 1 from both sides, and then I'm going to divide by 4. So I'm going to get x squared equals negative 1/4. Right. What values does x have? All right, so in order to isolate x, we need to take the square root, right? So we could say x equals the square root. And anytime we take a square root, we want to think plus minus, but we have a square root of a negative, okay? And so we could say that x equals plus minus 1/2 I, all right? However, this is imaginary, all right? And since it's imaginary, we don't see it on the XY plane. Like literally, we don't see it on the XY plane, all right? Now, if that is the only thing to consider, and we don't even see it on a real graph, are there any X values that will give us an undefined output? All right. And because we have only imaginary outputs, we can say that our domain is actually all values, all real values for x are okay. All right, all real values for x are okay. I take the square root of negative 1/4. Okay, so when we take the square root of a negative number, we're going to have an I. and the square root of 1/4 is 1/2. Okay. All right. Now, all real values for x is sort of a long way of saying this script-dr. Textbooks, they can print it real fancy, right? I just make it a script-dr by doing a double line for the sort of the long line down the R, and that symbol means all real numbers, okay? So this symbol is a way of saying all real numbers. All right. So once we find the domain, that's important because if we have a function, we need to make sure that it is continuous across the function. Because we know there's an imaginary number where it would be undefined. Okay, so actually that's a really good point. Negative infinity to positive infinity is another way of saying all real numbers. All right, so both of those would be acceptable. All right, because negative infinity and positive infinity actually only describe the real numbers. It does not describe imaginary numbers. Cool. All right, so let's see if we can find these critical points. All right, if we're looking for critical points, what do we know about the slope? Yeah, exactly. We know that f prime of x is going to equal 0, right? By definition, that's what we know about a critical point. So that means we have to take our derivative, we have to set it equal to 0, and we have to solve. All right. Now, if I wanted to take this derivative, I would have to use the quotient rule. All right, so let's set up that quotient rule real quick. We've got u equals the numerator, which is 10x, v equals the denominator, which is 4x squared plus 1. Then I get du is 10, dv equals 8x. All right. We're going to plug those into our quotient rule. We want to be really thoughtful about plugging it into the quotient rule and not the product rule by accident. So I have my v du minus u dv all over v squared. Okay. And I want to set this equal to 0, right? I want to know where that slope is equal to 0. Now, as gross as this looks, let's revisit another important concept, right? We said earlier that with fractions, we get an undefined output when the denominator equals 0. But I'm wondering if we can say something about with fractions, how do we get a 0 out? Because it turns out there's really only one thing we need to focus on. All right, so let's write that down. With fractions, we get an output of 0 when the numerator equals 0. All right. I'm writing that out in a sentence because so often we mix up these two rules. And I really want us to make sure we've internalized this, because even though this looks so gross, all we need to do is set that numerator to equal to 0. That is the only way we will get a 0 out. All right. So Let's do a little bit of algebra. I'm only going to grab the numerator. I'm going to set that equal to 0. And I'm going to distribute a bit, see what we get. 40x squared plus 10 minus 80x squared equals 0. I'm going to end up with 10 equals 40x squared. I'll end up with x squared equals 4. Correct or incorrect?
Incorrect, I guess. 1/4.
Yeah, we want to make sure as we're moving through the problem, if I'm dividing away, I want to divide by the 40. So 10 divided by 40 gives me 1/4. Okay. Now, when I take that square root, I better have a plus minus in the front. And the square root of 1/4 is 1/2. That means that we have 2 critical points. All right, we have 2 critical points on this graph, 10x plus over 4x squared plus 1. Okay. So what are our ideas? How could we tell whether this graph has a maximum or a minimum at those values? All right. We kind of talked about this a little bit yesterday, how we know. Checking the sign of what? Substitution of what? Let's be a little bit more exact in our wording. Okay, so we could take these values, we could plug them back into the original equation. We could certainly do that, yeah. And then if one of them is higher, that will be the maximum. And if one of them is lower, that will be the minimum. That's valid, all right? But I'm wondering if we can talk a little bit more about checking the signs on each side. What do you mean by checking the signs?
I just mean like on each side of those points of interest,
Yeah.
we check like the sign of the slopes, and then if it's like positive on the left side and then goes to negative, it's a maximum. And then when it's a negative and goes to positive, it would be a minimum.
Exactly, exactly. So that's actually, we could always plug it into the original equation, right? That will tell us whether we have a higher y value or a lower y value, right? But what we're hearing right now, this idea of tying this into slope, is that a local maximum, right? Let's zoom in a little bit. A local maximum will have a positive to 0 to negative slope. Right? If we think about a maximum, a positive slope to 0 to negative, that would give us a local maximum. If we think about it in terms of slope. Okay. Similarly, a local minimum will have a negative to 0 to positive slope. And we can sort of envision that negative to 0 to positive slope. Right? So as we are sort of learning these things, we want to learn how they tie into previous content. I think that's a little bit easier if we've seen this sort of story before, right? But all of this ties back to slope. And it ties back to slope because sometimes it's easier to work with the slope function than the actual function. Okay. All right, let's do one last problem here before we take a break. So this question asks us to write the domain of this function f of x equals x minus 2 or x minus x squared, all of that squared. And like the previous problem, it asks us to write the domain and then find the x values of the critical points and then explain one way to determine whether the critical point is a local maximum or a local minimum. Okay. All right, so let's ask ourselves the same question that we asked ourselves earlier, which is, are there any x values that will give us an undefined output? All right, so when we look at this, our gut instinct, do we have one? What are our thoughts? Because I don't know what this function looks like. Right. We could FOIL it all out, right? And if we FOIL that all out, what we're going to end up with is some kind of polynomial, okay? And so a point of interest might be for us to say that since f of x is a polynomial, all x values produce y values, right? Since f of x is a polynomial, all x values produce y values. And so Matt is correct. We can say, and let's write this in a number of ways, we can say that our domain is all real numbers, right? Fancy script R, that's absolutely fine. We could say it goes from negative infinity to positive infinity. That would be okay. All right. For those of you who are maybe looking to take some higher level math classes, like beyond Calc 3, where we really get into the theory behind all the stuff that we're doing, you might be more familiar with some of the set notation. You can say that x is an element of the real numbers, meaning x can be any real number. Or you can use that set notation that Matt had there, which is sort of a curly brace, x such that x is in the element, or is an element in the real numbers. That's fine too. Okay. And some people do that same notation, but they do like 2 dots instead of the line. And it means the same thing. Okay. I think most folks tend to stick with these first 2, and that is absolutely fine. All right. And some people have had, depending on their previous instructors, maybe their previous instructors wanted the set notation, and that's absolutely fine. Okay. How far did I go? I can. How far did I go in the math series? So I'm actually working on my master's in mathematics right now. So it has been definitely an experience. I think that the classes, so next year I'll be taking a bunch of graduate level classes on actually, believe it or not, like what we're talking about right now is more application. And then underneath this, there's like so much theory, more theory than you ever imagined was there. So ask me again in a year and I'll tell you it'll be further than it is now. Yeah. All right, so now we need to find the x values of the critical points, okay? And so if we think about what it means to find critical points, a nice way to summarize this is that we want to find the derivative and we want to set it equal to 0, okay? Now, I know that who suggested this earlier? Sherwin suggested that we take this function and we FOIL it out, right? We can certainly do that. Or what rule have we learned that would enable us to take this derivative?
Chain rule.
Yeah, that chain rule. All right, so we're going to use chain rule here. All right, so f prime of x is going to be the outer function, so 2x minus x squared to the first power times the derivative of the inside, 1 minus 2x. And I want this to equal 0. Okay. Now, I'm going to show you right now why it is actually better that we did not FOIL out. All right. If you FOIL out and you want to find where something equals 0 at the end, you're going to have to factor. And sometimes that factoring is harder than we want it to be. Okay. So chain rule is a nice way around that because look at what we have. We have 2 times something times something else equals 0. The only way this can equal 0 is if x minus x squared equals 0 or 1 minus 2x equals 0. 2 can't equal 0. Like this first number out here, 2, that can't equal 0. So I don't need to worry about that. But I do know that one of the things in the parentheses has to equal 0. Okay. So let's start with the right-hand side one, 1 minus 2x. I think we can see that if we add 2x to both sides, we get 1 equals 2x, and then we're going to divide by 2. So we're going to get x equals 1/2. And this is one of the critical points. Okay. I still don't know if it's a max or a min, but I know it's a critical point. Ooh, check out that spacing. Look at how close I am to the next page. Perfect. All right, so for the left-hand one, x minus x squared equals 0. How do we solve for x? What are our thoughts? All right. Okay. All right, so we know that 0 works, right? We can see from here just by plugging in 0 that 0 works. I would argue there's another number that also works.
Cancel out the number.
Yeah, 1 also works. Okay. So I want to make a point right here. I like to make lots of points, but I want to make a point right here about one of the most common mistakes that I've seen people do. I've seen people do this. Right? They add something to one side. It looks so much like what we just did over here. You add x squared to both sides, you divide by x, you get 1 equals x. Everything that you have here is mathematically correct. Why would I write that in red? Oh, the 1 came from dividing by x, right? So x divided by x gives you 1. Yeah, Evelina, what you have is correct, but I'm wondering if we can unpack why the red is incorrect. But why isn't this right though? Like, why should we have factored first beyond the fact that someone told us that we should have? There are multiple factors. So what happens here, you end up with one answer, right? But we know that there are two answers. And so what happens when we casually divide by x, oftentimes we lose a solution. Nothing worse than getting a question half right when you could have gotten it fully right, right? So we don't want to think about dividing by that variable, because as soon as we divide by that variable, we tend to lose solution. Rather, all right, let's do this in the green. We're going to write down what Evelina had there. She factored out the x. She was left with 1 minus x in the parentheses. And now she can say x equals 0 or x equals 1. And in the green, we are able to get both solutions. Okay, so a really small point that I find gets overlooked a lot when we're first learning about factoring and all of that. But it does become a problem now, because if we're looking for all of the critical points and we lose one along the way, we didn't get all the critical points. Okay. All right, so we are going to stop here for 4.3. All right, we're going to take a break.